session number 5 related to the bending moment and shear force. Previous sessions we discussed the bending moment and shear force diagram for different types of beams, cantilever beam and simply supported beam. And also I discussed the problems related to the combination of uniformly distributed load and point load. And previous session during the last, because of lack of time, I have skipped two problems I have explained. Just I have shown the problems. Let us discuss these two problems which is related to the simply supported beam having in combination of uniformly distributed load and point load. Afterwards in this session we will discuss the overhanging beam, single overhanging as well as double overhanging beam, and how to draw the shear force and bending moment diagram for that particular type of beam. Let us just see this problem, which is previous session itself I have shown this problem in which its load is symmetrical, that is entire A to B is loaded with a uniformly distributed load and also central point load. Since it is loaded symmetrically, that is 10 kilonewton is acting exactly at the center point, that is C. This RA and RA plus RB will be equal to the total downward load, that is 5 kilonewton into 3, 15 kilonewton plus 10 kilonewton. 5 into 3 is the uniformly distributed load plus 10 kilonewton is the point load. This is the total load acting on the beam. In this case, as already explained previous sessions, if it is symmetrical loading, this RA plus RB both will be equal to downward load and also RA and RB will be equal. Therefore, RA is equal to RB, that is 25 divided by 2, 12.5 kilonewton. See, 12.5 kilonewton takes RA and RB is 12.5 kilonewton. To draw the shear force diagram, first RB value minus 12.5 kilonewton, that is upward minus value. Then shear force at C, RB value is 12.5 plus half of the from C to B, whatever the uniformly distributed load is acting, that is 5 kilonewton per meter for a distance of 1.5. We have to take the right half of the portion because C, from the C right side whatever the load is there, that we have to consider. Therefore 5 into 1.5 plus 10 kilonewton is acting at the C point. Therefore shear force at C is equal to 5 kilonewton. Shear force at A equal to the 12.5 kilonewton, which is value of RA. How it is? 5 kilonewton is previous value plus next half from the A to C load is 5 kilonewton per meter is acting for a distance of 1.5 meter. 5 into 1.5, that is 12.5 kilonewton. This is about the shear force. Then to calculate the bending moment at B is 0 for simply supported beam. Bending moment at C, center point, that is 12.5 is the load at right side, that is a reaction, into moment is anti-clockwise, 12 into 1.5, distance from C to B is 1.5, 12 into 1.5 minus load, moment due to load is clockwise, that is why it is negative, minus 5 into 5 kilonewton per meter into distance is 1.5, right half of the portion, 5 into 1.5 into it acts, this uniformly distributed load acts at the center of 1.5, that is 1.5 divided by 2. Therefore bending moment at C is equal to 13.12 kilonewton meter. Bending moment at A is 0. Bending moment A and B are 0 and central point we have the value of 13.12 kilonewton meter. This is the shear force and bending moment diagram for this particular beam. What you can observe here, 12.5 is the RB value, here left side 12.5 is the RA value. Central drop is equal to the 10 kilonewton. You can observe here 5 kilonewton above plus and minus 5 kilonewton. Total drop is 10 kilonewton, and shear force changes its sign at the center point. Therefore, bending moment also maximum at the center point. And from A to B, because of uniformly distributed load, it is sloping. Shear force diagram is sloping. This is the shear force diagram. What you can observe here, wherever the point loads are there, that place drop is there, and wherever uniformly distributed load is there, that places inclined line. And then this bending moment diagram is very simple. Just draw an horizontal line and mark the midpoint value 13.12 and join with the parabolic curve. This curve should be parabolic. This is the case in which it is a combination of uniformly distributed load and point load. Next one, let us take one more last example, which is having a simply supported beam. Central this 2 point loads are acting 1 kilonewton and 3 kilonewton, and one more uniformly distributed load is acting at a distance of 1.5 meter from the support A. And what is the length of this uniformly distributed load? We have to calculate. Total length, this total span is 6 meter, and from A to this end of the uniformly distributed load is 4 meter. 4 minus 1.5, that is 4 minus 1.5 is 2.5. This uniformly distributed load is acting for a distance of 2.5 meter. And 2 point loads are acting from the uniformly distributed load, 0.5 meter distance, and another one is 1 meter distance from the next load. We have to take the moment about A for calculating the reactions at A and B. RB into 6, reaction at B, RB into 6, distance from A to B, and 3 into 5.5. I am taking a moment of all the load towards the A point. Okay, what is the distance from the A to the 3 kilonewton load? 4 plus 0.5 plus 1. 4 plus 0.5, 4.5 plus 1, 5.5. 5.5 is the distance, and 3 kilonewton is the magnitude of the load, plus 1 kilonewton into distance is 4 plus 0.5, 4.5, 1 into 4.5, and then 2 kilonewton per meter. 2 kilonewton per meter is the uniformly distributed load into distance 2.5. That is 2 into 2.5 is the total load acting, into distance from A to the center of uniformly distributed load. Center of uniformly distributed load is 1.5 plus center of UDL, that is 2.5 divided by 2. Then we will get the moment about A is clockwise moment is RB into anti-clockwise moment is RB into 6, clockwise moment is 34.75. Therefore, RB is equal to 34.75 divided by 6. We will get the value of RB as a 5.79 kilonewton. Now, upward forces is equal to downward force. Upward force is RA plus RB is equal to downward force is 3 kilonewton plus 1 kilonewton plus 2 kilonewton into 2 kilonewton per meter into 2.5 distance. Therefore, 9 kilonewton is the total load, downward load. RA is equal to 9 minus RB value. Therefore, 3.21 is the reaction at RA. We have the reactions at RA and RB. Let us calculate the shear force. Shear force at B. Shear force at B is minus 5.79, that is RB value. Shear force at C minus 5.79 plus 3 kilonewton downward load, 2.79 kilonewton, minus 2.75, because minus 5.79 plus 3 is the downward load, that is why we have taken as in positive. Minus 5.79 plus 3 is equal to minus 2.79 kilonewton at shear force at C. shear force at T, previous value is minus 2.79 plus one more load is added, that is 1 kilonewton. Therefore, minus 1.79 kilonewton is the shear force at D. Shear force at T, there is no further load is added between the E to D, that is why it is minus 1.79. Shear force at F, F point, minus 1.79 is the previous value plus 2 into 2.25. This is the load which is added, 2 into 2.25 distance. Therefore, plus 3.21 kilonewton is the shear force at A, and from A, shear force at F, from F to A no load is added, therefore shear force at A also 3.21 kilonewton. Like this we have to calculate the shear force for a simply supported beam. For bending moment diagram, bending moment at B is 0, bending moment at C, C point is from C to B distance is 0.5, 4 plus 0.5, 4.5 plus 1, 5.5 minus 6, distance is 0.5, 5.79 is the reaction into distance to C is 0.5, therefore 2.9 kilonewton meter is the bending moment at C. To calculate bending moment at D, again from D to B, what is the distance between D to E, B is 1.5, 1.5 into reaction at B, RB into 1.5, that is anti-clockwise, that is why it is negative. Then 3 into distance from D to C, D to C is 1 meter, 3 into 1, that is anti-clockwise, this is clockwise, 3 kilonewton is clockwise towards the D, that is why it is negative, minus 3 into 1, plus 5.79 into 1.5, minus 3 into 1, which will be equal to 5.7 kilonewton meter is the bending moment at D, D point. Next, bending moment at E, we have to take the moment of all the forces right side of the E, that is one is RB, RB into 2 meter distance from E to C is 2 meter, minus 3 into distance is 1.5, 3 into 1.5, minus 1 into distance is 0.5, 1 into 0.5. Therefore, 6.58 kilonewton meter is the bending moment at E. To calculate bending moment at F, instead of taking in right side of the F, I am taking the forces left side, which is easy because left side of the F is only reaction RB is acting, right side of the F is 2 kilonewton per meter UDL plus 1 kilonewton plus 3 kilonewton point loads are acting. We have to take the moment of all 1 kilonewton, 3 kilonewton as well as UDL load towards the F, or we can take the moment from the RA into distance. RA into distance is 3.21 into 1.5, that is equal to 4.82 kilonewton meter at the F, bending moment at F. Bending moment at A is equal to 0. This is the bending moment shear force and bending moment diagram. What you can observe here, this is the drop, again constant horizontal line, again drop of 2.79, 5.79 minus 2.79 is equal to 3 kilonewton drop is there, again here 1 kilonewton drop is there, 2.79 minus 1.79, 1 kilonewton drop is there, and then inclined line in between the uniformly distributed load, E and F uniformly distributed load is acting, that is why it is a inclined line, again it is horizontal because it is constant, and then you have to close the polygon. This is the shear force diagram for this given wave. And bending moment diagram, you can observe it is an inclined line, and then it is a parabolic line where UDL is acting, again it is inclined line E to D, again it is inclined line C to P. This is the bending moment diagram. I have solved these several problems for cantilever beam and simply supported beam carrying a uniformly distributed load, point load, and combination of uniformly distributed load and point load. By this you can easily, by seeing this calculations, you can practice how to draw the uniformly distributed load for simply supported as well as cantilever beam SFT and BMD diagrams. Now one more point is shear force changes particular point. You can see that distance we have to calculate. That is also I explained in previous session. Let us take this last example where x is the distance where shear force changes its sign. Therefore F to E is the distance 3 meter. Therefore 3 minus x is the distance where shear force changes its sign. You have to calculate the x value, then find the maximum bending moment by taking the moment about point where shear force changes its sign. Okay, let us discuss today overhanging beam. Overhanging beam means beam which extends beyond the support. You can observe this figure. AB is the supported points, span is L, and then from B it is extended. That extended portion is a overhanging portion where W load is acting. L1 is the overhang portion, and also you can observe second figure where two supports are there at a distance of L, and L1 is the extended portion right side and left side L2 is the extended portion. If beam is extended on both sides, it is known as a double overhanging beam. If it is beam is extended for the one side only, then it is known as a single overhanging beam. In this session we will see how to draw the shear force and bending moment diagram for the overhanging beams. I have considered one simple beam where 3 point loads are acting. One is at the free end 20 kilonewton and one more is at a distance of 6 meter from the A, and third point load is 2 meter from the A, left support. Two supports are at a distance of 8 meter apart. A and B is 8 meter distance and overhanging portion is 2 meter, and at the end of the beam 20 kilonewton is acting. This is the combination of simply supported beam and cantilever beam. This shear force diagram and bending moment diagram will be combination of simply supported beam and cantilever beam. Let us see how to calculate the reactions first. Since the supports are there, we have to calculate the reaction taking moment about A. Clockwise moments is equal to anti-clockwise moment. RB into 8, RB into distance is 8 meter is equal to, this is the anti-clockwise moment. Then all other loads will, if you take the moment, it will have a clockwise moment. 20 kilonewton also clockwise moment, all the 20 kilonewton loads, 3 loads will have a clockwise moment. Therefore 20 into, first one 20 into distance is 10, 8 plus 2, 10 meter. Next 20 into distance is 4 plus 2, 6 meter, and then 20 into distance is 2 meter. 20 into 10 plus 20 into 6 plus 20 into 2. Therefore RB is equal to 360 divided by 8, 45 kilonewton. RA plus RB is equal to total downward load 20 plus 20 plus 20, 60, 60 minus 45 will get the RA value as a 15 kilonewton, RB value as a 45 kilonewton. We have the values of reactions at support RA and RB. By having in reactions, we can calculate the shear force. Shear force at C. Now see, this is the extended portion. There is only one load is acting 20 kilonewton. That is why it is a plus 20 kilonewton shear force at C. Shear force at B, when moved towards the B, plus 20 is the previous value and 45 kilonewton RB value minus. It is upward load is we are considered as in minus, plus 20 minus 45, that is minus 25 kilonewton shear force at B. Shear force at D, previous value is minus 25 plus 20 kilonewton is added, therefore minus 5 kilonewton is the shear force at D. Again shear force at E, one more 20 kilonewton is added, previous value is minus 5 plus 20 plus 15 kilonewton shear force at E. Shear force at A also 15 kilonewton, there is no load is added in between the A to E, that is why it is a 15 kilonewton. Let us calculate the bending moment. Bending moment at C 0 because force into distance is 0. Bending moment at B, load is 20 kilonewton into distance is 2 meter, 20 into 2 minus 20 into 2 because it is a clockwise moment, minus 20 into 2 is 40 kilonewton meter. Bending moment at D, D point 20 kilonewton into distance is 4. Distance is 4. How it is 4? This is 2 plus 4, 6 meter is there. Here balance D to B is 2 meter. 2 plus 2, 4 meter. 4 meter is the distance of 20 kilonewton load from the C to D. This 20 kilonewton load and distance is 4 meter from D to C. 20 into 4 and then this reaction into distance from D to B. Reaction is 45 and distance from D to B is 2 meter. 45 into 2 is the plus because it is a anti-clockwise movement and minus 20 into 4 is the clockwise movement. Therefore, bending moment at D is equal to 10 kilonewton meter. Bending moment at E, whatever the loads are right side, we have to take the moment. These three loads, one is 20 kilonewtons at C and one more is 20 kilonewton at D and RB at B. Therefore, minus 20 into 8, this first load into distance from the E to the C, 4 meter plus 4, 8 meter, 20 into 8 minus value and then 45 RB value, 45 into distance 6 meter, E to B is 6 meter, since D to B is 2 meter plus 4 meter, 6 meter minus 20 into distance is 4 meter, 20 into 4. Therefore, bending moment at E is equal to 30 kilonewton meter. Or we can calculate the bending moment at E, RA into distance, RA into 2, 15 into 2, 30 kilonewton. Same we will get. Or we can calculate 15 into 2 from left side. Like this, and bending moment at A is equal to 0. What we can observe, calculation is similar to the simply supported beam what we did in previous sessions. While drawing the shear force diagram, you can observe, first you draw the horizontal line and then at C it is 20 kilonewton drop, vertical drop equal to the point load and it is remains constant up to B. It changes to negative value minus 25 and then it remains horizontal up to constant up to D and then it is reduced to 5. What you can observe, 25 minus 5 which is equal to 20. Drop is equal to, this drop is equal to 20 and then constant up to E, again it changes to plus 15. You can observe here plus 15 minus 5, therefore 15 plus 5, 20 drop is there, again it is constant and then you have to close. This is the shear force diagram. This left half of portion is like a simply supported beam, overhanging portion is like a cantilever beam. This is the combination of simply supported beam and cantilever beam. This is the shear force diagram. For drawing the bending moment diagram, first you draw the horizontal line and then minus 40, 20 into 2, minus 40 is the value of a bending moment, and then again it becomes a plus value, plus 10 at the D point, and then it is plus 30 at the E point. Now you can observe here bending moment is positive as well as negative, where what we have observed in simply supported beam, bending moment is positive. In cantilever beam, bending moment was negative. Here both positive and negative both are there. Now you join all the points. When you join the point, you can observe one particular point where bending moment is 0. Bending moment is 0 at one particular point. That point is known as a point of contraflexure. Point of contraflexure means it is the point where bending moment is 0 or bending moment changes its sign. This point of contraflexure occurs in overhanging beam only. We have not observed the point of contraflexure in simply supported beam, in cantilever beam. This is the point of contraflexure. We have to, sometimes in problems they will give, you have to locate the point of contraflexure. Let us see how to locate the point of contraflexure. This is the point of contraflexure, and we can take a distance x, where from B point, x distance is the distance where this bending moment changes its sign. That is, bending moment is equal to 0 at this point, at a distance of x from the B. As we have marked this as an O point, it is a bending moment is 0. That is O point, it will come somewhere here. This is the point. Okay, we have to take the moment about this point, right side or left side. Bending moment at O point, what are the loads are acting at right side of the O point? That is, one is 20 kilonewton into distance of 20 kilonewton to the O point is 2 meter plus x. 2 meter plus x. 20 into 2 plus x, and one more load is acting 45 kilonewton. 45 kilonewton into distance, O point distance is x. 45 into x plus 45 into x, because it is a anti-clockwise movement, and 20 into 2 plus x, it is the clockwise. Okay, when we equate this to the 0, because bending moment at O is 0, we will get an equation from which we can calculate the x value. X value is 1.6. 1.6 is the distance from the B point. From the B point at a distance of 1.6 towards the left, we will get the point of contraflexure where bending moment is 0. This is the one simple case. Another one simple case where only uniformly distributed load is acting throughout its length. This is the overhanging beam. Right side over its overhanging, 2 meter overhanging, and span, simply supported span is 10 meter, and 20 kilonewton per meter is the uniformly distributed load acting. Let us take the moment about A. Sum of the moment about A is equal to 0, or clockwise moment is equal to anti-clockwise moment. RB into 10. 10 is the distance from A to B, is equal to, there is the anti-clockwise moment, is equal to clockwise moment due to load. That is 20 into 12 is the total load. 20 into total load is acting up to distance of 12 meter. You should not take 10 meter. You have to add 10 plus 2, because this UDL is acting from A to B, full it is acting. If it is only it is acting up to simply supported portion, I can take 10. Here we have to take the 10 into 12 into 12 by 2. this uniformly distributed load acts at the center of the length, that is 12 divided by 2, 6 meter. Therefore, total moment towards A is 1440. 1440 divided by 10, you will get the reaction at B as a 144 kilonewton. To calculate the reactions at A, sum of the upward forces is equal to sum of the downward forces. Upward force is RA plus RB, downward force is 20 into 12. RA plus RB is equal to 20 into 12, that is 240 kilonewton. Therefore, RA is equal to 240 minus 144, that is equal to 96 kilonewton reaction at A. Reaction at B is 144. These are the reactions. After getting in reactions, it is easy to calculate shear force and bending moment. These are the two values. Shear force at C point, it is 0. Now point load, if it is point load is acting, then we have to take the value of that point load. Now shear force at C is 0. Shear force at B, you have to consider the load of right portion of B, that is 20 into 2, 20 kilonewton per meter into distance is 2. Total load is 40 kilonewton minus this load. At B, RB is acting 144 minus 144, it is upward, that is why it is minus. Minus 104 kilonewton is the shear force at B. Shear force at A, 96. Obviously it is 96, or you can calculate minus 104 is the previous value plus B to A. B to A, what is the load? 20 kilonewton per meter into 10, 20 into 10. If you calculate this, you will get the 96 kilonewton, which is equal to the RA value. Next, to calculate the bending moment at C is 0. C is 0. Bending moment at B, this right half of the right portion of the load, that is only distance of 2 meter, 20 into 2 is the load, and 2 divided by 2, which acts at the center of BC, that is 2 divided by 2, 1 meter from the B. This is the moment about B, that is minus value because it is a clockwise movement. Then bending moment at A is 0. A is 0, C is 0, B we have the value of minus 40 kilonewton meter. Let us draw the shear force and bending moment diagram. For drawing the shear force diagram, first draw the horizontal line. Then this is the point where total load is 144, out of which 104 is the negative value, negative is 104 and positive is 40. You have to show the drop equivalent to the 144, and the negative or rear force what we have calculated is 104. And here 96 is the shear force at A. Now you have to join this. Join from A to B and then B to C. Here you can observe this is the simply supported portion where shear force changes its one point. That point where we will get the maximum bending moment, we have to calculate the maximum bending moment at this point. And then here you can observe it is the cantilever portion. Cantilever portion is triangular shape. See bending moment diagram. To draw bending moment diagram, we have the this point we are not yet calculated. We have the value at the A as a 0 and C as a 0. At B is a minus 40 kilonewton meter. Just this portion it should be maximum. See, we have drawn all lines as parabolic line. You join from 0 to 40, which is parabolic, and join this middle portion where shear force changes its sign, and then it is not, it may not be, it is not a particularly, it is not a middle portion. We have to find the distance where it is, and then you join to the A point. Entire line should be parabolic because it is uniformly distributed load is acting from A to C. This is the point where bending moment changes its sign. Shear force changes its sign, there we will get the maximum bending moment. And also we have to locate the point where bending moment changes its sign, that is known as a point of contraflexure. Here we have the two tasks. First we have to find the maximum bending moment. To find the maximum bending moment, we can mark this point from left support or right support as an x. Then balance distance is the 10 minus x. Total distance is 10, out of which if we minus the x, 10 minus x is the distance from this point to the B point. Now these two triangles, x by 96 is equal to 10 minus x divided by 104. You have to use the shear force values of this particular point. Therefore, on simplification, we will get x value as a 4.8 from the A point. It is just in distance of 4.8. We will get the maximum bending moment. X is equal to 4.8. To calculate maximum bending moment, we can take the moment from A to the point where shear force changes its sign. That is, we can call it as a D point at a distance of 4.8 from the A point. Bending moment at D is equal to 96 into 4.8. 96 into distance is 4.8 minus this load 20 into, this is a clockwise load. If you take left side direction, you have to consider the clockwise movement as a positive, anti-clockwise movement as a negative. Reverse. If we are calculating bending moment from right side, clockwise will be considered as a negative, anti-clockwise positive. Here clockwise is considered as a positive and anti-clockwise as a negative. Minus 20 into 4. 20 into 4 is the distance 4.8. 20 into 4.8 is the distance up to which the UDL is acting, and 4.8 by divided by 2 is the distance where it acts at the center of the UDL. Therefore, bending moment at D is equal to 230.4 kilonewton meter is the maximum bending moment. Next task is to find the point of contraflexure. Let us, this is the point where bending moment is 0. It is just away from the B. We can take an x dash from this point to right side, or we can take left side. For what we can observe here, if we take left side, we will get only two load 96 and 20 kilonewton per meter is there. You can take anywhere. Now we are consider the x dash from the A to the O dash, A to the center point, this point where bending moment is changing. That point we can call it as an O dash. Okay, this O dash bending moment is 0. Let us take the moment about the O dash. What are the loads acting left side from the O dash? It is 96, 20. Or right side, it is a RB value and this 20 kilonewton per meter. Bending moment at O dash is equal to 0. That is 96 into x dash. X dash is the distance minus load is 20 kilonewton per meter into 20 kilonewton is acts up to the distance of x dash. 20 into x dash is the total load into distance from the O dash to the this UDL where it acts center, that is x dash divided by 2 must be equal to 0. If we simplify, we will get x dash as a 9.6 meter. That means this bending moment is equal to 0 at a distance of 9.6 meter from the A point, or it is 2.4 meter from the C point. This is the maximum bending moment value, and This is the point of counterflexure, that is x dash distance is 9.6 meter. Like this, sometimes we have to calculate the maximum bending moment when uniformly distributed load is given as well as point of counterflexure. One more example where uniformly distributed load is throughout its length plus one more additional point load is acting. Let us see how to calculate the bending moment and shear force diagram, shear force calculations. Taking moment about A, as usual, MA is equal to 0, RB into distance is 5 meter, RB into 5 meter, anti-clockwise movement is equal to, clockwise movement is first we will consider this 10 kilonewton into distance from A to C is 5 plus 2, 5 plus 2 is 7, 10 into 7 plus 20 into 7 is the total load, it is acting throughout its length, 20 into 7 into 7 by 2 which acts at the center of the 7 meter. This is the total moment 560 kilonewton meter. Therefore, RB is equal to 112 kilonewton. RA plus RB must be equal to the total load. Total load is 20 into 7 is the 20 into 7 plus 10 kilonewton is point load. Therefore, 150 kilonewton is the total downward load. RA is equal to 150 minus RB value. RB value we have already 112 kilonewton. Therefore, RA is equal to 38 kilonewton. We have the values of RA and RB. Let us calculate shear force. Shear force at C, now you should be familiar, that is 10 kilonewton acting at C. Shear force at B, 10 minus 112, and one more is UDL. UDL is 20 into 2, 20 into distance is 2. 20 into 2 is the one load, 112 is the RB and 10 is the point load. Therefore, minus 62 kilonewton is the shear force at B. Shear force at A, minus 62 is previous value plus 20 into balance UDL, 20 into 5. 2 already taken and balance is 20 into 5. 20 into 2 already considered in previous value and 20 into 5 is the balance. Therefore, 38 kilonewton is shear force at A, which is equal to the RA value. To calculate bending moment at C, 0, bending moment at B, right side of the B is 1 is 10 kilonewton is acting, 10 into 2 which is clockwise, that is why negative. One more is UDL. UDL is 20 into 2 is the load and which acts at the center of UDL is 2 by 2. Minus 60 kilonewton meter is the bending moment at B. Bending moment at A, 0. And somewhere we have to find out the maximum bending moment which may occur between the A to B. Let us draw the shear force diagram. What you can observe here, 10 kilonewton vertical drop, and here it is the 60 plus 50, 112 is the vertical drop, minus 62 plus 50, and then 38 is the RA value, and you can see it is inclined line because here uniformly distributed load is acting, and here also it is inclined line because UDL is acting, and vertical line here because point load is there. Here vertical line because RB is there. Here vertical line because vertical load of RA is there. And you can observe here, this is the point where shear force changes its side, where we will get the maximum bending moment. For drawing the bending moment diagram, you can observe simple. Here minus 60, it is parabolic curve, and then it is rises somewhere here maximum, and then again it is 0. This is the point where we have to find out the point of counterflexure. First we will find the maximum bending moment where it occurs certain distance of x from the left support, and balance is 5 minus x because total distance is 5 meter between A to B. Therefore 5 minus x is the balance between B to point where shear force changes its sign. Similar way, just calculate the x value. X divided by 38 is equal to 5 minus x divided by 62. We can get the x value as a 1.90. 1.90 from the A point where shear force is 0. This we can call it this point as a D point at a distance of 1.9 meter from the A. To calculate the bending moment, maximum bending moment which occurs at the D, 38 into distance from A to D is 1.9 sorry, which is the clockwise moment. Clockwise moment is considered as an here left from left side positive, and then this load 20 kilonewton per meter which is anti-clockwise, that is by minus 20 into distance is 1.9, 20 into 1.9 into 1.9 by 2 which acts at the center of the UDL, that is 1.9 divided by 2. Therefore 36.1 kilonewton meter is the maximum bending moment at D. And then to find the point of counterflexure, this is the point where it changes its sign. Let us call this as an O dash, which at a distance of x dash from the A. Bending moment at O dash is equal to 0. Find the bending moment at O dash, that is RA into distance is x dash minus this 20 kilonewton into x dash is the distance, total load is 20 into x dash divided by 2 which acts at the center of the UDL, that is x dash divided by 2 must be equal to 0. If you simplify this, you will get the x dash value as a 3.8. That means bending moment changes its sign at a distance of 3.8 meter from the A point. That is the point where which is called as a point of counterflexure. Like this, if a single overhanging beam is given, you should calculate the point of counterflexure also. And this is the maximum bending moment. Let us take next double overhanging beam. You can observe here why it is called a double overhanging beam. It is extended from the A left side 3 meter and it is extended right side 2 meter. Both the sides it is extended. That is why this type of beam is called as a double overhanging beam. Here a little bit you should be careful when you are calculating the reactions. Once reaction is calculated, it is easy to calculate the shear force and bending moment. First we will take the moment about A. Moment about A, RB into 8. RB is, this is the RB into distance. RB into distance is 8. We are taking the moment about the A, that is why from A to the B distance is 8 meter. RB into distance plus I have taken this is also 0.8 into distance is 3 meter. This is also anti-clockwise. This RB also anti-clockwise. And this 0.8 into 3 is also anti-clockwise. We are equating the clockwise movement is equal to anti-clockwise movement. Clockwise movement is due to 0.8 kilonewton as well as RB. That is why I have taken left hand side 0.8 into 3 is equal to 2 into the first we will take 1 into this is clockwise moment, 1 into distance is 8 plus 2 10 meter, 1 into 10, that is distance between A to C, and one more load is 2 kilonewton, 2 into distance from A to D is 5 meter, 2 into 5, 1 into 10, 2 into 10. These two loads will have a clockwise movement and 0.8 kilonewton is anti-clockwise, and this RB is also having a anti-clockwise. That is why clockwise movement is equal to anti-clockwise movement. That is the equilibrium condition we are using. Once you take the moment, you can easily simplify. RB is equal to 2.2 kilonewton. Just we are transferring all this 0.8 into 3 to the right hand side, and then divided by 8, we will get the value of RB. Then upward forces is equal to downward force. Downward force is 0.8 plus 2 plus 1. 0.8 plus 2 plus 1 must be equal to the RA plus RB. RA is equal to 3.8 kilonewton minus RB value. We will get 1.6 kilonewton as a RA value. We have the RA and RB value. Further we can move towards the calculation of shear force. Shear force at C, as usual, 1 kilonewton, which is downward, positive. Shear force at B, we have RB value minus 2.2 because upward, plus 1 previous value minus 2.2, which is minus 1.2 kilonewton is the shear force at B. When we are drawing the shear force, minus 1.2 downward, and then another 1 kilonewton balance. 2.2 minus 1.2 is 1 kilonewton, that should be upward. Total drop should be 2.2 kilonewton. Then shear force at D, minus 1.2 previous value plus 2 kilonewton is added, that is 0.8 minus 1.2 plus 2, 0.8 kilonewton. Shear force at A point, previous value is plus 0.8 and then minus 1.6, upward load minus 1.6, therefore minus 0.8 kilonewton is the shear force at A. Shear force at E, minus 0.8 kilonewton. Bending moment at C, 0. Bending moment at C is 0. Bending moment at B, minus 1 kilonewton into 2, that is distance, 1 into 2, minus 2 kilonewton meter. Bending moment at D, load is 1 kilonewton is acting at a distance of 3 plus 2, 5 meter, minus 1 into 5, and then RB is there, plus RB 2.2 into distance is 3 meter. This is the total moment about the D point. Then bending moment at A, we can take left side, 0.8 into distance 3 meter, which is anti-clockwise, minus 0.8 into 3, minus 2.4 kilonewton meter. This force into distance 3 meter. We can take from left or right side. When we are taking left side direction, you have to change the sign of convention. This is the bending moment diagram. You can see this center portion is the UDL portion, and there is this simply supported portion, and this is the cantilever portion. This is also cantilever portion. You can observe shear force changes its sign at this exactly at the D point. Therefore, maximum bending moment will occur at this point only. And then mark the values of bending moment at D as well as B as well as A. You can observe here two places bending moment changes its sign. We have to find the point of counterflexure at the 2 points. One side we can mark the x distance from E to the B point and take the moment about the E of all the loads. We will get the point of counterflexure as at a distance of 1.6 from the B point. Then mark one more x point from the RA value, A point, and again take the moment about the F and equal to 0, we will get the point of counterfracture distance as in 3 meter. Okay, like this we have to find the 2 point of counterfractures if it is in double overhanging beam. Okay, this is just I am not going to discuss, just I will show you if it is in double overhanging beam with the uniformly distributed load throughout its length. It is a symmetrical loading. Just I am determining the RA, RB and RA is same as how we can take the moment, or just divide the total load. Then calculate the shear force at the various points. Then calculate the bending moment. Afterwards, if you draw the shear force diagram, you can observe here central portion is the simply supported portion, and also you can observe everywhere it is a sloping because it is a uniformly distributed load, and also shear force changes its sign exactly at center since it is a symmetrical loading, and 2 overhanging portions you can see. This is the just like it is cantilever beam, and also this is a entire this bending moment diagram is a parabolic curve, and it is having a 2 point of counterfractures. We have to find the point of counterfracture. First, considering left side, we will get 4.74 by equating the total moment about the F is equal to 0, and similarly you can calculate the point of counterfracture right side, or since it is a symmetrical loading, x will be same for right side as well as left side. You will get the quadratic equation. From that you can solve the problem. Okay, this is how we are discussed elaborately related to bending moment and shear force chapter. Next session we will discuss bending stress. Thank you.